The bisection method in mathematics is a root-finding method that repeatedly bisects an interval and then selects a subinterval in which a root must lie for further processing. It is a very simple and robust method, but it is also relatively slow. Because of this, it is often used to obtain a rough approximation to a solution which is then used as a starting point for more rapidly converging methods. The method is also called the interval halving method, the binary search method, or the dichotomy method. The method is applicable for solving the equation f, x, a equals a0 for the real variable x, where f is a continuous function defined on an interval, a, b, and f, a, and f, b, have opposite signs. In this case a and b are said to bracket a root since, by the intermediate value theorem, the continuous function f must have at least one root in the interval. At each step the method divides the interval in two by computing the midpoint c equals /2 of the interval and the value of the function f, c, at that point. Unless c is itself a root, there are now two possibilities: either f, a, and f, c, have opposite signs and bracket a root, or f, c, and f, b, have opposite signs and bracket a root. The method selects the subinterval that is a bracket as a new interval to be used in the next step. In this way the interval that contains a 0 of f is reduced in width by 50% at each step. The process is continued until the interval is sufficiently small. Explicitly, if f, a, and f, c, are opposite signs, then the method sets c as the new value for b, and if f, b, and f, c, are opposite signs then the method sets c as the new a. Equals 0, then c may be taken as the solution and the process stops. In both cases, the new f, a, and f, b, have opposite signs, so the method is applicable to this smaller interval. Iteration tasks: the input for the method is a continuous function f, an interval, a, b, and the function values f, a, and f, b. The function values are of opposite sign. Each iteration performs these steps: calculate c, the midpoint of the interval, c equals 0.5. Calculate the function value at the midpoint, f, c. If convergence is satisfactory is sufficiently small, return c and stop iterating. Examine the sign of f, c, and replace either, or, with, so that there is a zero crossing within the new interval. When implementing the method on a computer, there can be problems with finite precision, so there are often additional convergence tests or limits to the number of iterations. Although f is continuous, finite precision may preclude a function value ever being 0. For f, x, equals xai euro, there will never be a finite representation of x that gives 0. Floating point representations also have limited precision, so at some point the midpoint of a, b, will be either a or b. Algorithm: the method may be written in pseudocode as follows. Input, function f, endpoint values a, b, tolerance tol, maximum iterations nmax, conditions, a, b either f, a, 0 and f, b, 0 or f, a, 0 and f, b, 0, output, value which differs from a root of f, x, equals 0 by less than tol. NA1, while NA-per-mil currency NMAX limit iterations to prevent infinite loop, CA/2 new midpoint, if f, c, equals 0 or /2, tol then solution found, output, c, stop, end if, NaN plus 1 increment step counter, if sign, f, c equals sign, f, a then AAC else BAC new interval, and while, output, method failed. Max number of steps exceeded. Example, finding the root of a polynomial. Suppose that the bisection method is used to find a root of the polynomial. First, two numbers and have to be found such that and have opposite signs. For the above function, and satisfy this criterion, as and. Because the function is continuous, there must be a root within the interval, 1, 2. In the first iteration, the endpoints of the interval which brackets the root are and, so the midpoint is. The function value at the midpoint is. Because is negative, is replaced with for the next iteration to ensure that and have opposite signs. As this continues, the interval between and will become increasingly smaller, converging on the root of the function. See this happen in the table below. After 13 iterations, it becomes apparent that there is a convergence to about 1.521 a root for the polynomial. Analysis: the method is guaranteed to converge to a root of f if f is a continuous function on the interval, a, b, and f, a, and f, b, have opposite signs. The absolute error is halved at each step so the method converges linearly, which is comparatively slow. Specifically, if C1 equals /2 is the midpoint of the initial interval, and Cn is the midpoint of the interval in the nth step, then the difference between Cn and a solution C is bounded by. This formula can be used to determine in advance the number of iterations that the bisection method would need to converge to a root to within a certain tolerance. The number of iterations needed, n, to achieve a given error, I micron, is given by, where, therefore, the linear convergence is expressed by, see also, secant method, Newton's method, root finding algorithm, binary search algorithm, Lemma-Eurosha algorithm, generalization of the bisection method in the complex plane, nested intervals, Brent's method, references. Burden, Richard L. Fez, J. Douglas, 2.1 The bisection algorithm, numerical analysis, PWS Publishers. ISBN A0-87150-857-5A. Corliss, George, which root does the bisection algorithm find? Siam Review 19, 325 €327, doi, 10.1137/1019044, ISNA 1095-7200A. Core, Author. Kalu, Egwu, Numerical Methods with Applications. External links, Wellstein, Eric W., Bisection, MathWorld. Bisection Method Notes, PPT, MathCAD, Maple, MATLAB, Mathematica from Holistic Numerical Methods Institute, Module for the Bisection Method by John H. Matthews, Online Root Finding of a Polynomial Bisection Method by Farhad Maizalumi.